Uh, Hello everyone. Our topic is implementation and analysis of the information bottleneck. I'm Sera Neha Murtha and my teammate is Revant Valluru. So today we're going to start with the problem statement block diagram. So here we take the input x. We start with the input variable x, which is a high dimensional data, and then the aim is to compress this data by finding a simpler representation t. This happens by minimizing the mutual information between t and x, meaning t should retain as little as unnecessary detail from x as possible. Bottleneck t. T becomes the bottleneck, the compressed representation. Relevance preservation. But we don't want to lose meaningful information, so at the same time, we maximize the information between t and y. So, output y. Finally, the goal is that t helps us predict y effectively. So, overall, the information bottleneck method balances compression and relevance, compressing x while keeping only the parts that matter for predicting y. Now we move on to the slide 2, proposed approach for block diagram. So this slide explains the algorithmic steps we implemented to solve the information bottleneck problem. So we start with the distributions P of x and P of y given x. These define the joint behavior of inputs and labels. And then we compute the initial P of t given x. We initialize a random or uniform mapping P of t given x. Then the algorithm enters the iterative updates, updating P of t, updating P of y given t, and then updating P of t given x. These updates gradually move t forward and the optimal bottleneck representation. After the convergence, we obtain the optimized bottleneck representation of t. We then compute the I of x, information between x and t and information between t and y for various values of beta to understand the trade-off between compression and relevance. Finally, we visualize these values on the information plane to study how well the bottleneck performs and validates the behavior of algorithm. So this workflow shows how we implemented the information bottleneck algorithm end to end and analyzed this performance.
Let's look at slide 4, which represents the core results of our implementation. The centerpiece of our validation is the information plane plot. Here, the x-axis shows information between x and t, the mutual information between the original data x and our compressed bottleneck representation t. This axis represents compression. A value closer to 0 means we have successfully discarded more irrelevant information from x. And the y-axis here shows information between t and y. It is a mutual information between the bottleneck t and the target output y. This axis represents relevance. A higher value means our compressed representation still retains a lot of meaningful information to predict y. What we actually see in this plot is a fundamental trade-off of the information bottleneck method. Each method on this curve represents a different run of our algorithm with a unique value of beta. It is a parameter that controls the trade-off. As we increase beta, we tell the algorithm to care more about preserving predictive power. The curve moves up and to the right, we see information between t and y increases dramatically, meaning t is becoming much more better at predicting y. But this comes at a cost of reduced compression, as information between x and t also increases. This curve also visualizes the entire premises of the method. We cannot have the perfect compression and the perfect relevance. Coming to the slide 5, here we have our conclusions, contributions, and future directions on this slide. In summary, what we actually implemented is information bottleneck framework from the ground up. Our algorithm effectively takes high dimensional data and derives compressed representations that strategically preserves the information most essential for prediction. This information plane plot serves as clear evidence that we have captured the core compression relevance trade-off and contribution with compared to base paper. This work provides a complete implementation of the information bottleneck algorithm, including mutual information, estimation, and iterative optimization, along with a clear visualization of the compression relevance trade-off, future direction, or possible confidence details. Efforts may extend the approach to variational formulations, apply the method to real-world continuous datasets, and iterate the information bottleneck principle into deep learning architectures. Thank you for hearing us out and providing this wonderful opportunity to demonstrate our video.